Welcome to another installment of the Robinson Twins present Earth is Our Spherical Home Planet. In this installment, we'll look at how rockets work even in the vacuum of space. Now, we grew up in the 60s and 70s and saw a lot of rocket launches, and it confused us a little bit about how rockets appear to push off the ground with their thrust, but then once it gets into the air can't offer as much resistance as the ground does, so it didn't make sense. We had to look up how rockets actually work, and then it all made sense. First, let's start with Newton's third law of motion, which states for every action there's an equal and opposite reaction. And it's important to note forces always occur in pairs. That will be very important later. Now let's look at it in terms of balanced versus unbalanced forces. This rock has a mass of 1 kilogram. If we round off the acceleration caused by gravity, that's 10 meters per second squared. Multiply those together, and we get 10 newtons. So that means I have to apply 10 newtons of force in the upward direction with my hand to keep it from moving. So with these forces balanced, the rock won't fall. If I applied more force, it would go up, but if I let go, it will drop. That was in slow motion. Here it is at regular speed. So now the forces are unbalanced. So gravity wins. Now let's look at another situation involving forces, and that's a balloon. When you fill it with air, the air pushes off in all directions and they end up canceling each other out until you let air out. Then the forces become unbalanced. The air going out no longer has any effect on the balloon. It's the air forces on the other side that win. Let's look at it again in slow motion this time, and remember that forces always act in pairs. Now all the other forces in the balloon cancel out, but the one that pushes forward and the one that pushes it in reverse do matter, because as soon as I let go of the balloon, the air that would push it in reverse escapes, no longer having any pressure inside the balloon, and the force on the opposite side that pushes it forward wins. Now let's see how this applies to rockets. In the rocket you have the fuel and an oxidizer, and together they will make a chemical reaction. In the combustion chamber you get an explosion, and forces push off in all directions, and they cancel each other out, except there's a force pushing forward and a force that would push in reverse. But the force that would push in reverse leaves the rocket altogether and no longer has any effect. It can't cancel out the forward force. I think I really have to emphasize this because I've seen even science YouTube channels and science programs on television talking about how rockets work, and whenever they say it pushes off the ground or it pushes off the air, that's wrong. That's not how it works. The fact that the exhaust gases are exiting through the nozzle means it's not pushing against anything. The exhaust pushes against nothing. And the reason why the rocket moves is because the forward force that could be canceled out by the reverse force isn't canceled out, so it wins. The forward force wins because there's nothing canceling it out. Here's a YouTube channel called Lab Rat that does a very good job explaining it. Check this out.
Now here's what the pressure profile looks like inside the rocket motor. First of all, we have combustion, and that creates pressure forces on the top of the casing, on the bottom of the casing, on the front, and the back of the casing. Now, the upward and downward forces don't contribute to the leftward force creating the thrust in this picture, so we can eliminate those. And also, if you look at the right-hand side of the motor, there's a hole at the back end. Now, there's no surface for the pressure to act on, so there's no pressure force acting in the area of the throat of the nozzle. So if we eliminate balanced forces again, we see that we have a leftward force created by the pressure inside the casing. There's also a pressure inside the nozzle, exit cone, and this acts perpendicular to the surfaces. If we break those pressures up into components, eliminate the up and down forces that don't contribute to the actual thrust of the rocket motor, we see a pressure force on the exit cone of the nozzle. Now it's these leftward acting forces that are actually the thrust of the rocket motor.
Imagine that these opposing forces are like a tug-of-war. The blue team is providing a forward force and the red team is providing a reverse force. But what happens if the red team all lets go? They are no longer providing any force in this tug-of-war and they are gone. Reverse force missing, the forward force wins. And that's what happens in a rocket engine because there's a nozzle. Here's a rocket test in the vacuum chamber done by the Action Lab.
Hey, it worked! Look how cool that looks. You can see the stream of smoke particles shooting out of the rocket like a laser beam. Since there's very little air in the chamber, there's nothing for the stream of gas to bump into, so it has a very straight flow with little turbulence. So if we were at this pressure in the sky, we wouldn't be able to use a traditional jet engine to provide thrust. We would have to use a rocket. Rockets not only work in a vacuum, but they actually work better in a vacuum than at atmospheric pressure. The propulsion in a rocket comes from the fact that you're expelling gas out the nozzle of the rocket at high speeds. In order to conserve momentum, that means that there has to be an equal and opposite force on the rocket in the opposite direction. This is similar to how a strong hose pushes you backwards due to the water being forced out of the nozzle. This is happening with rockets, except that its gas is moving at ultrasonic speeds being shot out the nozzle.
Now we just know that someone watching this video is going to point out the fact that this smoke reached the wall, but how does that help the rocket? It doesn't. The gases, once it leaves the nozzle, is no longer part of the rocket at all. Hitting the wall makes no difference. It may apply a force over here on the wall, but that doesn't translate back to the rocket at all. That's why we feel the need to keep repeating this so that people understand it. Even science programs on YouTube and on TV programs I've seen get this wrong. The push in the rocket is inside going forward. The gases leaving the nozzle aren't canceling it out. That's the important thing to remember. It's just like the tug-of-war I showed earlier. The team that let go of the rope is the hot gases leaving the nozzle. They're not applying a force to the rocket at all anymore. They may be applying a force to the ground below the rocket, but that doesn't do the rocket any good. It's the force inside the rocket that's not canceled out. The tug-of-war team that won the battle. So the question we had as kids was, does the rocket push off the ground? No. Does it push off the air? No. The push is inside the rocket, and what comes out of the nozzle is a reverse force that's being discarded, essentially, and the forward force wins the tug-of-war. So as long as combustion happens, the fuel and the oxidizer join and combust. It can happen in water. It can happen in air. It can happen in the vacuum of space. What's outside the rocket once the hot gases leave is irrelevant to the rocket. I hope I made my point clear. Now, if you like that kind of content, be sure to like and subscribe. And if you had rockets explained to you in a way in this video that you'd never heard before, and it really starting to make sense to you, give us a like and subscribe. Thanks for watching.